Hey everyone. Thought I'd do a chair stream. Alright, kill that. Alright. Who's ready for some serious algebraic topology? Oops, wrong one. Don't do that. What? Alright. Okay. Make myself nice and small. Hello. There's that sweet algebraic topology. Hey, Dragon Drake. Excellent. Tyson. Hey, everyone. Thought I was always on this side. Except maybe the first lecture or two. Weird. Alright. Make sure this is, it's a little bit weird. Why is it chopped off the top? Maybe it was doing that all the time. Oh no, it's this. Okay. Okay, sorry. I rode back from uni in a hurry. So I was trying to not be so puffed out. Come on streams, come on chats. All right, window management done. Okay. Okay, so we last time just looked at geometric realization, which is a process of getting a topological space from a delta set. I'm just going to quickly, so I hope everyone saw the well, at least the link to the video that I put up earlier today on YouTube. I'm just going to drop it in the stream chat when my internet can find YouTube. Come on, YouTube, come on. Alright. Where's the get a shareable link? Sweet. Okay. Sorry. That's the link. Yeah, so I encourage everyone to watch that. I went through in slow detail exactly like geometrically what's going on with the process. I mean, it's 20 minutes and I did the boundary of the 3 simplex. So that's not time I can really spend in class doing it, so have a look. Yeah, I made one small simplification which doesn't actually change anything. I just these 2 maps here I collapsed into one map. It's not a big deal. Okay, so I was sort of rushing towards the end, but the important thing I want to note is this whole thing is functorial. And in the scan notes, I kind of indicated what it would look like. So yeah, I drew a cube. Let's see. I recommend you go look at the scan notes. Basically, universal property of a push-out iteratively constructs the function f here. So you get a sequence of maps. So these partial steps. And because it arises from this universal property, it's continuous by construction with the topologies involved. There it is. No, where did it go? Oh, okay, yep, here we go. And then the collection of all of these gives a map between the unions, which is like the full geometric realization, and then the way that the sequential colimit topology is defined. That map is automatically continuous. And in fact, these are like, there's uniqueness here in these universal properties, and this is what you use to prove that this whole thing is functorial. So when you compose, so this bit, this is a big implication arrow that implies that you get a uniqueness, which is enough to show, or you get two functions, two continuous functions, and they both satisfy appropriate conditions which force uniqueness, so those two functions have to be the same, and that's where we get this equality here. Okay, so let me just record that as a more formal proposition. It goes from delta set to topological spaces is a functor, and also it has some nice properties. So what does it do? If you take the disjoint union of delta sets, it gives you the disjoint union of spaces with appropriate topology. Probably isomorphism here. Why don't we go? Yep. The geometric realization of the zero simplex is the one point space. So if XA is a pair in the technical sense of delta sets, so A is a sub-delta set of X, we get is a pair of spaces. What does that mean? It means that the injective function here is a subspace embedding. Because the inclusion map of A into X as delta sets gives on geometric realization a continuous map from the geometric realization of A to the geometric realization of X, and that map is continuous, and the result is that this is not only injective, but A has the topology inherited from X. Sorry, geometric realization of A has the topology inherited from the topology of the geometric realization of X. Okay. So these are some nice properties of this thing. So yeah, that's cool. Space Getter, it is something like that. We have, I mean, category of delta sets is not quite as nice as one would hope. It's like a toy model of the thing we really care about, which is simplicial sets. But certainly we had a functor going the other way from a space to a delta set, which took, you know, your space, and then the k simplices in the delta set are all the continuous maps into X from the topological k simplex. And so these functors are related, but in a complicated way. What else do we have? So we have some examples. I think I mentioned above. Sorry, let's squeeze. Oh yes. So I'll just mention again the geometric realization of the delta set n simplex is homeomorphic to the topological n simplex. If you look at, I mean, yep, it's fine. If you think about this property here, then you think about the n-1 skeleton sitting inside delta n here on the left hand side. We get a we get, as it turns out, the topological boundary of this, which is, let's say it's the points x0, xn in the topological n simplex, such that one of the coordinates is 0. So, yep. So you can think about this in terms of the 2 simplex. Its boundary is part of the 2 simplex that lies in one of the coordinate planes, and that's a triangle. What else do we have? We have this nice result, which is important for technical result that I'll mention, but I'm not going to go through in great detail. So I didn't generically define what like the Cartesian product is of delta sets, but we looked at what this one was. So I mean, for the purposes of this course, this delta set, the squiggle underline is just some technical instruction which we gave a name. But like the picture that I drew, great, now I'm not going to be able to draw it. Something like that. Yes, okay, that's right. Whatever I drew, like this was just a cartoon, so I could remember the sort of combinatorics of all the labels. When you geometrically realize it, it becomes these 3 tetrahedra glued together like this, like as a topological space. So equals 2. So for instance, our friend P infinity, this geometric realization is an infinite dimensional space. So these examples that I've written down before, they're finite dimensional. So whatever infinite dimensional means, I'm gluing together n simplices for arbitrarily high n. Okay. But a complicated one, like P infinity is weird. It's certainly not infinite projective space. Okay, so one thing that I do want to note, yeah, Chris, I mean dimension as in like the maximum dimension of n simplices that I glue in this geometric realization process. So it's not like pure n dimensional, because I can have, you know, Like this counts as two-dimensional because it's like the maximum dimension of a simplex in the geometric realization. You can even have some single points out here. It's a bit like how at the start of the course combinatorial surface meant like at most two-dimensional. And like this can be like weird and singular, you know, like in you know, like this sort of thing is not a manifold by any stretch of the imagination. It's sometimes a manifold. I mean, but we only glue it together in a continuous way. So you'd have to choose a smooth structure or something. I mean, there's a condition you can put on your delta set such that it becomes a topological manifold. Even a PL manifold, which is a slightly better than topological manifold, but generically it can be singular and weird. Okay, so here I just want to note, so let's say I've got an n simplex in my delta set X. Then what this tells me, I have a map in the construction of, so here I think of Xn as a discrete space, and then given this X here, I get an injective continuous function sending this is just the topological n simplex sits inside this product space, and then as the iterative construction of the geometric realization, I have this map phi n, and that sits inside the full geometric realization, and so I get a composite map which is continuous. I might call this like x hat. So the combinatorial data of an element of the set of n simplices in the delta set, purely combinatorial, I get an actual topological n simplex in the topological space. So this should strike you as maybe a very useful fact, because I've taken something like I have a combinatorial model for a space, and each thing in the combinatorial model gives me an actual topological thing that I'm thinking of. You know, I'm thinking of little x here as an n simplex, but it's not actually an n simplex, but it gives me an actual n simplex when I geometrically realize. But what this tells me is that, and if I have different little x's, then they have disjoint image inside this product here, and so I get distinct, like if I have x and x prime, then I get x hat and x hat prime. They are different functions. So this means I get an injection, a one-to-one function from the combinatorial n simplices of x to the topological n simplices inside its geometric realization. Okay. Any questions? And while I write down the next thing, you can write down your questions. I'll also note, this is a fun exercise, this set Xn is the same thing as the Hom set. What was the key point for brevity? Geometric realization is a functor, and I get this injective map. And I note, maybe for interest, is that right, this delta set delta n has a single n simplex, and a map of delta sets has to send that somewhere, and what it sends it to is, well, something in xn, and then because it's a map of delta sets, all the lower dimensional data is automatically determined. So this gives us so what I do is I evaluate my function of delta sets on the single n simplex in delta n, and that gives me something in xn, and that's an isomorphism. Yeah, so Chris, yeah, so top blah blah is the Hom set in the category of topological spaces, and same here for delta set. And this map, this function is the geometric realization functor, what it's doing on Hom sets. Oh. So this is kind of a side note, but it's not just plucked out of the air, it's like absolutely baked into the formalism. But yeah, the fact that xn, big Xn, gives a subset of all the actual topological simplices inside its geometric realization is key. Because what I can do is so even better, these maps, right, these functions give a map of delta sets from X to, well, it was this S construction. Yeah, that's it. And it's in fact like a sub delta set. It's injective dimension. I mean, that's something you have to check, but it comes from, it's a little bit involved, but it's something you can check. It's the compatibility of the face maps for the topological simplex and the combinatorics of that, and how it relates to the face maps of X. Okay, so this is maybe where I wrote the thing was key. The key maybe is this bit. Right, because last lecture, my whole motivation of, well, attempted motivation of this whole procedure is, how do we compare, no, sorry, let's say that again. If I claim delta sets are combinatorial models of spaces, how do I relate them to actual spaces? So the thing is now, if I make an actual space, then I have a way of calculating cohomology from an actual space. So in what sense does the delta set, or the delta set has cohomology, so in what sense does that cohomology tell me something about the space? Yeah, so the S is the thing that looks like, well, it's the delta set which in each dimension, or let's say n, is this. Oh, sorry. Yeah, so I defined it for metric spaces before I defined topological spaces, assuming that people had kind of seen what metric spaces were, and we're happy to talk about continuity of maps from like delta n, which lives inside Rn plus 1, to a metric space, because you just need like epsilon delta continuity. But now we can talk about arbitrary topological spaces. So lemma, I call this a lemma in my notes. I'm not going to prove it. But then I have a map of delta sets, so I can get a map of cochain complexes. I've written it the wrong way in my notes, but that's okay. All right, let me write out this lemma. Map of cochain complexes. So the whole point of trying to make everything a functor is that you can just keep composing functors. So once I say, oh, I've got a map of delta sets, then I've got a map of cochain complexes, then I've got a map on cohomology, and these things compound. So you can, and at every stage, everything compatible with composition and so on. It's like a massively modular algorithm. If you've seen functional programming, and I know at least one person in the class has, this is like the mathematical version, and in fact kind of the theoretical origin of like that whole functional programming mindset. You know, map reduce, all that kind of stuff. Map of cochain complexes. Because now, how do I want to write this? So this is like the singular, and there's probably meant to be some R's somewhere around here. So by singular, I mean the thing built out of these topological gizmos. So this is like R, S. Now, like this thing is like massively huge and uncountable, and so then functions out of that to R is even bigger. The thing on the left hand side could be like finitely generated free modules. This is huge, and this is small. Okay, and then here's the theorem, and then I shall attend to my nose. And we're going to prove this theorem. We've got to go on a bit of a journey to get there. And this is maybe one of the key theorems in the course. So I'm giving it to now so we can appreciate how awesome it is. So a finite dimensional delta set. So it has no n simplices after a fixed point. This map, this comparison map, is a quasi-isomorphism. So we will prove this. So this is a hot theorem. And I will leave you ponder that and write me some questions while I sort out my my issue. Chris, yes. It was in the guise of SM. And the tutorial last week sort of was dealing with it, but also trying to see what extra mileage we could get out of the construction. So it's actually better than a delta set, but we're just considering its delta set structure. Can't quite remember where it was. It was Probably at the end of the delta set section before we started homological algebra, if I sort of remember. Yeah. Let me check. Just trying to sort out examples of delta sets that weren't boring. Delta set. Yeah, looks like lecture 11. That was a while ago, but it's a delta set because of the maps like partial I that go from like delta, like topological k minus 1 simplex to the topological k simplex, like the various boundary components. Okay, so this is a big theorem. Because if I have a space and I know it's the geometric realization of something, then I can calculate its cohomology using the delta set. So say y is homeomorphic to geometric realization of x for some delta set x. We can calculate the cohomology of y. And even better, right? Maybe x is a finite delta set, in which case it's like finite dimensional linear algebra. I mean, if R is a field, it's really linear algebra. If R is Z, then maybe it's like groups and so forth, but it's not so bad. Okay, so we're going to need some tools for this. Okay, so there's a couple of biggish results that we need that are kind of I'm going to treat as a black box, because the proofs are like highly technical and, you know, take like a lecture and a half, 2 lectures to prove, and the technique of the proof is not like massively illuminating for the purposes of like learning cohomology. It's like, well, I have this specific construction in mind, and it's pretty gnarly, and there's all kinds of little bits of input, and in the end you get a result that is totally believable, and which you can use without knowing the guts of the proof. So we have 1, 2, let's see, there's one of them, yeah, 2 basically. Two of these, and we'll just, you know, I'll kind of verbally indicate maybe how the philosophy of the proof. Like Hatcher does the details of the proofs in the version, the homology version, so you can at least look at it and go, okay, that's what's involved. And the proofs aren't the same, but it's using some of the same techniques. Okay, so first thing I want to do is get a Mayer-Vietoris theorem for topological spaces. But before we can get that, we need something else. So, all right, what is Mayer-Vietoris? Mayer-Vietoris is, well, if I have some, for the delta set, if I have like a push-out square of delta sets where all the maps are injective, then I get a long exact sequence in cohomology of delta sets. So I want something similar but I want to make my space as a push out of open subsets. So I'm going to fix X a topological space. These are open subsets. We get a push out square. Basically, this is down to a special case of the gluing lemma that we had last lecture. So the intersection of two open sets is open, so this U intersection V is also an open subset. More generally, these could just be like injective functions that are subspace embeddings. That's okay too. The machinery can't tell the difference. So then, like you might think we get from this a short exact sequence. We don't. What we're going to do is we're going to take part of the short exact sequence and make the rest, and then try to link it back to something we already know. So we have, let's see, we start from the right. So we get, and so I'm going to put like a subscript sing on everything for singular, which is to remind us we're in the topological world. And I'm going to omit the R coefficients everywhere now because there's a lot. Yep, so we get a map the other way. Right, so I have this map, and what does it do? It takes, remember, a thing in here is a function on the enormous set of all the simplices sitting inside these spaces. What I can do is restrict, so my F to things that just land in the intersection, and I restrict my G to the things that just land in the intersection, and then take their difference. So this function takes a simplex in the intersection and then evaluates it on F and on G, and then takes their difference. Okay, so this map turns out to be surjective. I mean, I've kind of hinted it's going to be so, but this is. So it's an extension by zero property. Chris, yeah, it's so when we define the next thing, I mean, because the naive thing is to do this, right, is to put the cochain complex for X there, but this doesn't work. This really doesn't work. So what you do, go that, just take the kernel, just like take the kernel of this map, because it's onto, you take the kernel, and then you know you have a short exact sequence. So I did this a little while ago. Let's say you had any surjective, like level-wise surjective map of cochain complexes. You can take all the kernels, and then everything assembles into a short exact sequence of cochain complexes. And so the trick is, what is this kernel? So I'm going to give it some notation. So it depends on U and V, this open cover. I forgot to write U union V is all of X. Otherwise we don't get a push out square. Yeah, so what we would like, Chris, is the thing involving X to be exact, but it's not. So we're going to play a trick. I'm going to define this new thing. So we're just going to define this kernel level-wise. It gives us a cochain complex, and we're going to give it this notation. So like C bullet, but with a UV subscript of X. Now, here's the clever part. Blah, 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 blah. Yeah, so I have a little remark about how we can see this is surjective in my written notes, and you can have a look at that. And we can show, this is not terribly difficult. This turns out to be isomorphic to those functions. It's not that, it's like Cn uv x is isomorphic. Right, so this is so a thing in here is in singular cochains on X, but I have a requirement. If I have a map from an n simplex into X, if it doesn't factor through one of your V, then I want my F to be 0 on that simplex. So I'm going to give these things a name. I'm going to call these large simplices. So this sort of special kernel cochain complex is isomorphic to the submodule of C singular of X that of functions that are 0 on large simplices. So and in fact it's a sub cochain complex. Right, so it's like a sub cochain complex. Right, so what does a large simplex look like? Let me just draw you a picture. All right, I need some. So let's say U is this bit, and maybe I'll give that some shading, and then hopefully for contrast everything here in this speckled region this is V, and there's an overlap. Okay, thanks dear man. Just wanting some contrasting, even if visually, not color. Okay, so U union V is all of X here. The whole thing is X. So a large simplex is one that doesn't fit neatly inside U or inside V. It has to somehow spill outside U and outside V. So, all right, so it's going outside, it's going outside U on this side, and it's going outside V on this side. So it's a large 2 simplex. So if it was entirely inside sort of the blue speckly region on the right, or if it was entirely inside the yellow stripy region on the left, it'd be a small simplex. So I'm only considering those f's that return 0 on such large simplices. Okay, so then here's my black box theorem. I'm going to call it a red box theorem, where red is for tricky. Tommy, 5 lines down my page, that very phrase appears. But the problem is, I'm thinking here of functions on all possible simplices. So I can't just ignore the large ones. All I say is my functions ignore them. I can't ignore them, they're still there. So here's the theorem. So this is a submodule. It's true for all R. So this concept of quasi-isomorphism is hugely important. Okay. So what does it mean? Every element in this singular cohomology, so the cohomology coming from sort of topological cochains here, so some function on all large simplices sigma. Okay, so that's kind of profound. Like, that's not a formal property because it somehow knows about the topology on X and, you know, which simplices are sort of inside U, inside V, and their intersection, and, you know, it's, and you're looking at all the simplices at once. So if you want to change like your representative of your, oh, please no, I had a vague idea of trying to get a different iPad today at work. That's a flashback. Not happy, Jan. So let's write it out again. Anyway, it's highly non-obvious how you would prove this. So the proof uses barycentric subdivision, which is a technique where you cut up like your topological and simplex into strictly smaller copies of itself. Well, like things that are homeomorphic to it but sit inside it. And then these are all actually tetrahedra inside here. So you can prove that all of these get strictly smaller by a certain factor, and as you iterate, they shrink. Their size is bounded above by a certain factor, and so you can prove they get smaller and smaller. Use the Lebesgue covering lemma to make sure you've chopped up the simplices small enough that they all fit inside U or V. But this is the idea, vague idea of the proof. In practice, it's not that simple. Hatcher takes like 4.5 to 5 pages to prove basically this theorem in the homology case. So compare. I'm not saying this is a good idea, but you can compare to Hatcher's proposition 2.21 for how much work it is. Non-examinable. Okay. So the thing that I lost is this short exact sequence, which is probably a good idea that I write it again anyway. Right, so by definition, this cochain complex arises as the kernel of the map, this map. And if I forget to write a sing somewhere, it's because I forgot, not that it's important. Yeah, Chris, like 2 minutes. So from this, we get a long, it's a short exact sequence of cochain complexes, so we get a long exact sequence. But I've got these weird things here, so everything's singular, and I'm omitting the R's, but they're there. So bullet, these are bullets. Anyway, it's a 2-hour slot. We've got to H1, let's call this delta prime, not 1, U, and so on. Same story, except this leftmost column is a bit weird. Who knows what that is? Singular. So I'll leave you all to ponder this. I don't know what that squiggle is. And I will fix this one up because it's janky. And the maps are standard ones that we've been seeing. Okay, so we've got to fix up this long exact sequence because whatever this leftmost column cohomology group is, it's weird. All right, well, let's have a break. And 5 minutes at most. And then, yeah, and fire away questions in the chat, and on Discord too if you want. I've got them both open. I should maybe write break time. Yeah. Anyways, what's new? Oh yeah, JSX. I went to my favorite cafe in town and got myself a nice coffee for the purposes of going to write this juicy material. Exchange. Yeah, the exchange is pretty fancy, Tyson. Oh, Space Kitty, yeah, totally. This is like the fat geometric realization. Or if you like, there's a map from the semi-simplicial category covariant functor to topological spaces, which gives the topological delta simplicity, topological simplices. And then you have the Onader embedding into delta sets, and then you can't extend its geometric realization. Yeah, Tyson, the exchange is like it's pretty nice. Although I once was in there, this is some years back, and someone was in there talking to their friend, and they're like, "Oh yeah, until this place opened, there was no good coffee anywhere in Adelaide." At which point it was like, "Okay, this place is like, you know, hipster central." Because I don't know, Italian coffee culture in Adelaide has only been around for like 50 years. So yeah, I like Larry and Lad purely for the fact I can get $1 off if I take my own cup, and it's actually the most cost-effective coffee. Yeah, not sponsored, not sponsored. It's a sweet, very nice coffee, very nice staff, and they, yeah, $1 off. Take your own. Got myself a free coffee today, filled up my card, so that was even better. Yeah, I can't remember the last time I had a Blend 43. That was my go-to when I was a teenager, but just can't. All right. But yeah, it's best cafe is so subjective. All right. Well, we've been here 5 minutes. Hey, now these people are saying no cafes in Adelaide were any good ever until the exchange turned up. That's just a bit strong. Man. Yeah, I got home a bit too late. Well, I didn't really need another coffee. I just had a really good one. I mean, I used to drink Turkish coffee when I was a teenager. Took up the pot. I think I once accidentally bought two. I went out to the Central Market with someone and bought us both one. The Perfect Cup. This is like 17 years ago or something. 2 Turkish coffees, and the other person didn't actually want it, and so I drank both of them, and that was yeah, it's probably the first time I had a midday coffee and had trouble going to sleep that night because it was strong. I mean, I have a friend who just doesn't drink coffee ever. He's Greek background, and his uncle or something gave him a Greek coffee when he was little, and it just scarred him for life. So anyway, break time's over. Who is it? Chris is back, I hope. Oh yes, you're back. All right, let's roll. So what we have is this long exact sequence. It's not the Maia-Vietoris sequence because yeah, I drink stacks of tea as well. I mean, like big mugs of extra strong Yorkshire tea or whatever. Like ideally like 2 before work. Right, but this is not a Maya-Vietoris thing. Let's get back into headspace, into like maths. Because these things, let me just right, box them. Right, this gizmo and this gizmo and all the way down. This is not, on the face of it, a priori, the cohomology of X. It's the cohomology of this weird cochain complex, which gives 0 value to all large simplices. But I did have the result that this map is a quasi-isomorphism, and I have better. There's a commutative triangle. Like so. I mean, the thing I wrote and then crossed out earlier, U, C, V, and then this thing. I do have a commuting triangle here. That's a pretty bad commuting triangle. Everything's singular. That's not my funky thing that I don't really understand. And this map is a quasi-isomorphism. So when I apply cohomology, what I get is singular cohomology of X and the cohomology, let me just specific dimension, the cohomology of my funky temporary cochain complex, whatever that is, and they both map to the cohomology that I'm interested in, which is U. I live dangerously, do some erasing, plus V. These are singular, singular. So I do have a commuting triangle, and I know this is an isomorphism. Yep, that's the right way around. And moreover, I have my this connecting homomorphism from the cohomology of the intersection at n-1. And so what I could do is define sort of a new connecting homomorphism, which goes to the full singular cohomology by delta prime this way, followed by the inverse here, and then the induced map from the singular cohomology of X to here is the same as that in the forward direction, and then the map I actually have in my long exact sequence. And what this tells me is that, so this is exact. But the long exact sequence is exact here. So the image of my delta prime is the kernel of the next map. But that's enough to say that it's exact at star. So I get a new sequence where I've swapped out the cohomology of this slightly peculiar cochain complex for the actual singular cohomology of X that I wanted, and I don't break exactness. So I do have to check this, because if I start replacing things with isomorphic groups and I'm not careful about the maps, it's not clear that the kernels and the images will line up right when I replace something by something else that's isomorphic, because you've got to know what the maps are to get exactness. Okay, hence, here's a theorem. This is Maya Vietoris for spaces. Open cover UV of X, get a long exact sequence. And now this is the real cohomology of X. Probably insert magneto meme in here. The meme content on Discord has been nearly non-existent, so it's mildly disappointing. Maybe everyone's just working too hard, which okay, that's fine. Okay, H1 XR and so on. So it's like Maya Vietoris, but now it's everything's topological. There's no delta sets in sight. Come on, Tyson. Eric, probably it's not Magneto in the meme. Eric, oh, I can't remember his surname. Yeah, Charles in Discord, that's it. I mean, the real singular cohomology of X. Okay, and so I also note we get the same with singular cohomology everywhere. Singular. Reduced. This is already singular. And I should. This is. So for spaces, we don't even need to choose a base point. We can define it. No, need more space. No. Yes. So remember, PT is the 1 point space. And this map is induced from the standard map, from any topological space to a single point, which is always continuous. Singular cohomology is a functor, and you get the whole Maya Vietoris thing. Okay. I don't have another app, Space Kidder. That's the problem. This is not my iPad. I mean, I don't have an iPad. And my own tablet is not compatible with my computer. And yeah. Some people at work have fancy new big iPad Pros. So, I mean, I don't even have admin. I don't know if I got the Apple account password that this is like registered under. Okay. So this Maya Vietoris for topological spaces, it's hugely powerful. I mean, the real OG result is this one. This black box theorem gives Maya Vietoris. It also gives a bunch of other things we'll see later. But Maya Vietoris, don't do that. Maya Vietoris comes out of this without a massive amount of effort. Okay. So, I've got to give some more technical content. So, So I need some prep before I can give the black box theorem. So let's say f and g are functions, continuous functions topological spaces x and y. So a homotopy from f to g is a continuous function h product topology on the interval times x to y such that h of 0x equals f of x, h of 1x equals g of x for all points little x and big X. So you should think of this then like the parameter t in the interval. It sort of as you increase it from 0 to 1, it deforms f into g continuously. So like for each t, htx is a continuous function of x. It's a continuous function from x to y, and it somehow interpolates between f and g. So yeah. So there's a formal similarity to a cochain homotopy, but not in this form. There is a way to do it, but that's a discussion for offline. So let's have an example. So let's take identity from the n disk to the n disk. I should define what this is. X in Rn of length at most 1. So D2 is the closed unit disk in the plane, and I'm going to do the 0 map for want of a better. It's a constant function that takes the value 0. Okay. Then also shorthand, I'm going to write I, capital I, as the unit interval. So the function which takes a tx to 1 minus tx as possible, these are just vectors, is a homotopy. So when t is 0, that's the identity from identity to 0. Yeah, so there's a formal definition of like a homotopy in a category with some structure. Well, there's left homotopy and right homotopy and all these various variants and different ways to axiomatize it, but they all kind of give the same information. When are two functions close enough to each other that we should really think of them as being the same? All right, and if you think of topology as being somehow everything's kind of squishy and up to deformation, then functions that can be deformed into one another should somehow not be too different. Yeah, so this is that's a word you can use, Chris. So, I mean, you have to think, why is it continuous? But everything here is just like a subset of Rn or Rn plus 1. And so think about continuity in terms of like sequences or epsilon deltas or something. I think last time I taught this, I was like how do you even know it's continuous in terms of like the definition of continuity just of a topological space with like inverse images of open are open, and I ground it out. It was mildly painful, but you can use sequences here. Take any two functions, f and g, x to say Rn, so the notion of homotopy is symmetric, right? Because you can replace t by 1 minus t, so it flips like g. There's a homotopy from f to g or a homotopy from g to f. It doesn't matter. So there's like a homotopy between them. Sorry, take. This is true for an affine space more generally. Presumably something like any locally convex topological vector space. If you know what that is, it works. But so they're a little bit boring. I mean, the spaces here are kind of not very interesting, but more importantly is the following. Maybe this is sort of one thing we can get. And here's another thing you can do. So this is, we've seen something like this before with cochain complexes. So a continuous function, I'm just given one continuous function from x to y. It's called a homotopy equivalence. If there is some function in the other direction with the following property, there exist homotopies let's see, f compose g and identity on y, and g compose f and the identity on x. So they're like inverses, except they're not actually equal to the identity, they're only homotopic to the identity. So I should say what homotopic means. So terminology. Given the above definition, f, g, h, say f and g are homotopic. So I'm not mentioning what h is, I'm just saying there exists one. Yes, but if I have an h, a specific one, I say that's the homotopy from f to g. So here I'm just asking, I just ask that some g exists and some homotopies like h and h prime exist. Okay, and then we say x and y are homotopy equivalent. If at least one such f exists. I mean, they can be homotopy equivalent in different ways. You could pick a different f and get different homotopy equivalences. It's like saying a group has automorphisms, like it's isomorphic to itself in different ways, or like two groups are isomorphic in different ways. Okay, so for example, I can map Sn minus 1. Well, this sits inside Rn. I'm going to take Rn and rip out the origin. And there's a function going the other way, which takes So this is the inclusion map, and this one takes an x and sends it to the same thing but divided by the length. Now because x is never 0, then this is well defined and it's a unit vector. So the homotopy equivalence. I have similar to before. I mean, these are like injective examples, but they don't have to be. There's a single function from Dn back down to this sort of 1-point space. So Dn is homotopy equivalent to a point. I mean, same thing is true for Rn. All right, let's see. And so we say this is like a special case. So if x is homotopy equivalent to the 1-point space, we call it contractible, because we can shrink it down to a point continuously without crushing any holes or what have you. Okay, so contractible spaces turn out to be not so interesting. So here's the other black box theorem for today, or I should say red box theorem. So this color is red. So again, the proof of this is doable at the level of this course, but I don't have like the time to spend digging into the technical guts of the thing. And if you need to know the technical guts, then you are studying this in enough detail that you can go and do it yourself. So given a homotopy H between f and g, both continuous functions between topological spaces x and y. All right, so I've got an h here. I'm going to have another h soon. Let's not write down that h. So f and g induce maps on cohomology because cohomology is a functor. So we're given this. We have two induced maps. Let's call them HNF, HNG. So HN is a contravariant functor. Oh, this is like singular. You have two induced maps like this. Given the homotopy, we know that these maps are the same. So given f and g, we have two maps, and given the homotopy, we know the maps have to be equal. So there's a vague proof outline. very vague. We want to first, you reduce to the special case where y is I times x, and you have the following functions, I0, which goes from x to I times x, and I1 so now you just prove it for the special case of these two maps, and these two maps, there's a homotopy between them, namely so I0, I1 are homotopic via, well, what's the function you can write down? It's the identity map. This is the homotopy between I0 and I1. So already you can see this is a massive simplification. General case follows because you have I times x h to y, I0, I1, this composite is G, and this composite is F, and you use that, you have a functor. So on cohomology, you apply cohomology, and the two maps here become equal, and therefore this map and this map is equal, but that's F and that's G. So that's the general case. So how do you think about the special case? You have to cook up a cochain homotopy, which is now a purely algebraic thing, but you do it very, very carefully. So you take this one here, it has to map to Cn minus 1 of x. Alright, and it uses n-dimensional delta set, the n-dimensional delta set delta 1 times delta n minus 1. Something like, so let's suppose you're given sigma from delta n minus 1 into x, and you need to evaluate something on it. This is the same as the geometric realization, delta 1 times delta n minus 1. But then inside here, there are n simplices in the combinatorial sense, and so there are topological n simplices inside the geometric realization. These are explicitly constructed, like coordinates, like literal coordinates. And so the composite from this topological n simplex here all the way down to here means you can then evaluate something here on it. Anyway, there's this whole intricate construction, and you have to then check that it is a cochain homotopy, and it is a cochain homotopy between the correct maps of cochain complexes. And like I said, it's technical, but it boils down to knowing this this n-dimensional delta set structure that we defined earlier in the course, and it's basically bookkeeping. So the proof in Hatcher is, I I can't remember where it is. He does the homology version, but you get to see some of the ideas. Anyway, yeah, we actually have done enough in this course that you should be able to read a proof of this and it will make sense. Okay. All right, so a corollary of this theorem, so that's like end of not really proof. A corollary is if I have a homotopy equivalence, and this is really the part we care about. The other one's good, but for the purposes of this course, this is the one you should really think about. If you have a homotopy equivalence, right, and now we need a specific homotopy equivalence, not just we know one exists, we want a specific one because we want to apply a functor y to x well, in fact, we can say better. It's like an isomorphism of graded modules, but this is isomorphism of R modules. Same thing for all n. So this is using the theorem and functoriality. Now, see a space kidder. Sorry, having troubles with the technology. Proof, use theorem plus functoriality. So you have a map G going the other way, and then the induced linear map on cohomology from G is the inverse to this map here. Okay, so that's awesome. Any questions? Small stretchy break. Ugh. So we've done some pretty serious stuff today. I mean, I think that might be the last of the serious black box tools. But once you have those, you can then, like, we can now really start to crank up the calculations. I mean, the whole long exact sequence thing, and knowing this thing about homotopic maps and like topological Moivre torus, we can start to turn the handle, and all the homological algebra starts doing work for us like nobody's business. Right? Because, for instance, how do you think you calculate the cohomology of a sphere, like a singular cohomology? Like, it's defined in terms of these massively infinite dimensional modules that are functions out of some uncountably large sets, and then you have these crazy maps, linear maps between them. It's, you know, there's no rhyme or reason that says that these should be sensible. Yeah, so Chris, you know, and so it's clear that like the two sphere doesn't have a three-dimensional hole, right? Because you just count the one hole in it. Or that the second stable homotopy group of the spheres should be trivial, as like Pontryagin thought. They published a paper, it's like, it's trivial. And then it turns out, actually it's not. You know, this is from the definition. I think I gave an example, you know, like what's the, yeah. Grothendieck had a great quote where he was just doing really hardcore abstract theory, and he says people won't care about this unless I come up and calculate like S153, sorry, like the 153rd homotopic group of the 67 sphere or something, random numbers. And he's like, people care about that stuff, but I don't. But it's really, really hard to calculate these things. Cohomology, we can do it now. All right. So, as an example of this, so let's apply this. We get that the K, I have to switch to K now, the singular cohomology of the point, values in R, as isomorphic to the singular cohomology of Rn for all K, isomorphic to the singular cohomology of the disk. I mean, these things are enormous. You know, these, that's an Rn. You think about it, this is some quotient module of some uncountable dimensional module, free module. And yet, turns out we can calculate it as the singular cohomology of a point. Sweet. Do we know what the singular cohomology of a point is? I mean, it's turns out it's like still our old friend cohomology of P infinity, which you have calculated. So that's pretty awesome. I mean, you write down what the singular cochain complex is of a point. It turns out to be the cochain complex of P infinity. We also have things like singular cohomology of Sn minus 1. So this one's maybe, there was an allusion in the chat to electromagnetism and magnetic monopoles. This was this isomorphism essentially was used by Dirac in like 1931 or 1933 or whenever it was, to write down some interesting solutions to the Maxwell equations for like k equals n equals 3 and k equals 2 or something. So here's another example. So one corollary of functoriality, which I may not have mentioned, but a functor sends an isomorphism to an isomorphism. So it sends a isomorphism of delta sets. Like the cohomology modules are isomorphic. Homeomorphic spaces, their cohomology modules are isomorphic. So everything's kind of nicely preserved in that way. And I can write down a homeomorphism. This is going to be important in a little bit. Let's take an n sphere and remove its north and south poles, where they are the points with coordinates are plus or minus 1 in the last slot. I can write down an explicit homeomorphism to Sn minus 1 times this interval here. Homeomorphism, what does it do? It sends x0 up to xn. Yep. To now I truncate my vector. Now since xn itself is never 1, at least one of these other things has to be non-zero. So I can normalize this. And then I drop my last coordinate in that spot there. And you might have fun reconstructing what the the other continuous map in the other direction is like. When you think, okay, why is this continuous? Again, everything's kind of sitting inside Rn, so you can use sequential notions of continuity. And so, and here's another fact: if y is contractible by some homotopy, then x times y is, let's say, the projection map onto x is a homotopy equivalence. Nice little exercise to see why that's so. And so in particular, so this unit interval here, open unit interval, is contractible because you can just shrink it down to the point continuously. The projection map to Sn minus 1 is a homotopy equivalence. So we get singular cohomology. It's n minus 1 times minus 1 1. It's isomorphic to the singular cohomology of Sn minus the 2 points, which is also isomorphic to the singular cohomology of Sn minus 1. Okay. All right. So these are things we can say. So it seems kind of like pushing bubbles in the rug, where we're sort of got something complicated and we push it and it's going somewhere else, but we're doing it in such a way, we're setting it up so that we can actually use all these little seemingly gimme funny little facts to do a real computation. So someone remind me, the calculation of the cohomology of P infinity, that was assignment 2, wasn't it? Don't want to give away the answer if I'm having a mental blank and it's secretly okay. Alright, so the cohomology of P infinity was trivial except in dimension 0. So here's another example. So if y is contractible, so everything also works with reduced cohomology. So y is contractible. So here's a fun fact. It's reduced cohomology, reduced singular cohomology is 0 for all k. It's because well, this is isomorphic to the reduced cohomology of a point, and this is the same thing as the ordinary singular cohomology of a point, not reduced. They're only different in dimension 0. This is like hk of p infinity r equals 0. This is for all k not equal to 0. And what about when k equals 0? Y is isomorphic to h singular cohomology of a point in dimension 0. But what is this? This is now the co-kernel of the map from the point to the point. That's the identity map, which equals 0. Okay, awesome. So we've done a lot of theory. Now the dominoes are starting to fall. We can actually start to say something non-trivial. I mean, if you think about it, this P infinity is like an infinite dimensional thing. Well, okay, in the delta set world, it's an infinite dimensional thing, but its cohomology is trivial. And here I'm extending this kind of result to say any contractible space. Contractible spaces can be very large, as in, you know, infinite dimensional topological vector spaces. So their cohomology is, on the face of it, it's a quotient of some unbelievably even more infinite dimensional modules. Cool. Okay, so we can now calculate singular cohomology, kth dimensional singular cohomology of the n-sphere. All right. Who wants to do it before the end of the lecture? I think we can do it. There we go. Different set of notes. Making good progress. Actually, this is probably not so bad. No, okay. Yep. I'll do this one on the top of my head. It's that easy, relatively speaking. So we're going to cover Sn by open sets Sn minus North Pole, and you can check this as an open set. Well, what is the topology on Sn? I haven't really said. It's the topology induced from Rn plus 1 and from the standard topology on Rn plus 1. In particular, you can do something like the complement of a point in Rn plus 1 is open, because you can use like the metric definition. And then we intersect that with Sn and get an open set. And you take your point in Rn plus 1 to be this capital N, or to be capital S here. So these are open subsets. And their union is all of the n-sphere, because n and s are different. Then U intersection V is the n-sphere minus both the north and the south poles, which we know is isomorphic to Sn minus 1 times some open interval. Moreover, we know that U, using stereographic projection, so this is a thing that takes a sphere minus this point and maps it down to a point in the plane. So there's a formula you can write down. I'm happy to supply it later. So this is homeomorphic to Rn. V is homeomorphic to Rn, involving a slightly different map. Viatorus. Let's write it down with reduced cohomology. Viatorius. I'm going to leave off the singulars and the H0U, H0V, reduced, H reduced U intersect V, what is this? 1 H reduced 1 V U intersection V. Right, now I want to write out a generic bit. It's going to be here. Let's say ... That's HK minus 1 U, HK minus 1 V. It's all reduced. H reduced K minus 1 U intersection V. H reduced K SN HK U HK V, so on. Okay, so fact 1, U and V are contractible because they're homeomorphic to Rn. So then this is 0 for all k. Oh wow. So first up, this implies, so that's a 0, that's a 0, that's a 0, that's a 0. And so our long exact sequence splits up into short sequences. Also, I know that this first map here is injective, so H twiddle 0 Sn equals 0. I could reconstruct regular H0 later. And then I get H twiddle K minus 1 of U intersection V, but what is that? I know that's Sn minus 1 times an interval, but the cohomology is just that of Sn minus 1. Sn minus 1 H twiddle K Sn 0. Now this is exact, so I must have that this is isomorphic. Okay, that's pretty impressive. I've got some induction possibilities happening here. So let me fix let's take k equals n to start with. Try k equals n. Well, so this means that you can work down the isomorphisms Hn Sn all the way down is isomorphic to H twiddle 0 of S0. S0 is the disjoint union of 2 points. So we, I think, can calculate the cohomology here. And it turns out to be, well, it's cohomology plays well with disjoint unions because it maps out. Yeah, there's a reason. I'll maybe cover this elsewhere, but you can write down what the reduced cohomology is. This is equal to R. So it's for all n. Okay. Bam. That's pretty impressive. So we've got that one. That one. I mean, that's impressive enough. I think I will come back at the start of next lecture and fill in the gaps. But we've already calculated 2 cohomology groups that from the definition would have been unthinkable to calculate. I mean, from this I can say, non-reduced cohomology is equal to R, and because n here is, let's say, for all n greater than or equal to 1, this is equal to regular Hn Sn. So this is enormous progress, and I've black boxed the technical bits that actually do the work for us, like the really technical bits. But this is the calculational ability just like ramps up once you have enough tools. You can start calculating things just using formal properties. Cool, so we'll stop there, and I look forward to seeing you tomorrow, or you'll see me tomorrow. I will say, do check out the little extra lemma I dropped in Discord. I'm going to pop it on Canvas, probably under the resources. No, I'll pop it in the next to the appropriate lecture. I'll pop it next to the, oh no, I'll pop it in the resources, just like extra resources module, so you can see it's not too hard to track down. And otherwise, have fun on the assignment. It's I'm more than happy to discuss with people, answer questions. All right, catch you later.